Hello, my name is Jacob Logan, and today I will be discussing adaptive controls in additive manufacturing processes. In 1984, the first additive manufacturing machine was introduced to the industry by utilizing 3D models and mirroring the layering that takes place in topography mapping. This process was called stereolithography, or SLA. Since 1984, large technological advancements in additive manufacturing have occurred rapidly. In the early 2000s, some startup companies developed do-it-yourself kits to introduce consumers to the world of additive manufacturing. Today, we're beginning to see additive manufacturing become usable for not just prototyping, but actual end-user parts that can be installed in airplanes and cars. Recent advancements in additive are even enhancing the material engineering realm. The company Mark Forged has developed a proprietary continuous fiber reinforcement, or CFR, method that is strong enough to replace any metal fabricated parts. The challenge in this new manufacturing process, where material is built up into three-dimensional parts, is that the quality and consistency of the finished product. This makes adaptive controls critical to the varying additive processes. Different batches of material can have inconsistencies in their composition, creating variation in the quality of the final product. Inconsistent temperature can create warping, stress fractures, and porosity. Layer by layer fabrication must be consistent and aligned to ensure that the structure will be strong and not fracture. Another challenge that additive manufacturing has always dealt with is the ability to control the layering in a way that provides a smooth surface finish. By advancing adaptive controls, the industry can mitigate these challenges and increase the quality, consistency, and productivity for the manufacturer. The Encyclopedia of Physical Science and Technology states that an adaptive control system is one in which the controller parameters are adjusted automatically to compensate for changing process conditions. In order to implement adaptive controls, there is a need to understand what the key process input variables are and what their optimized state is. Then, a system of controls that automatically adjust the KPIs can be implemented into the process using sensors, machine learning, and even artificial intelligence. The intent of this presentation is to explore new advancements that are being made in adaptive controls for manufacturing, to understand the current state of those controls, and to look to the future for how controls can take additive manufacturing to the next level in Industry 4.0. One of the ways that adaptive controls has been implemented into additive manufacturing processes is via in situ monitoring controls. In situ process monitoring means that the control monitoring and adjusting is done directly where manufacturing occurs. This optimized form of controls is done using optical-based monitoring, acoustic-based sensing, laser line scanning, and X-ray monitoring. Laser additive manufacturing processes such as laser powder bed fusion, or LPBF, and laser directed energy disposition, LDED, can be complex and defects can be difficult to mitigate. In LPBF, it is a challenge to achieve a fully dense part with zero porosity due to the stochastic nature of the process. It is also limited to small parts due to its limited build volume in the build chamber and low build efficiency. The process is also extremely sensitive to powder characteristics and control parameters. Also, the high thermal gradient stemming from rapid heating and cooling can induce stress and distortion in the material. LDED uses a higher voltage and therefore is capable of creating larger parts from 3D models. It is also capable of adding material to existing parts, making it a workable solution for repairs. That said, LDED has its limitations as well. The high thermal input and large melting pool creates a coarse microstructure, reducing the mechanical strength of the material. One of the ways that these limitations have been mitigated is through the use of vision-based monitoring. Digital and infrared thermal imaging can identify defects during manufacturing and feed that information back to the adaptive control system to automatically adjust parameters. Acoustic-based monitoring is another in situ control that can be used in laser additive manufacturing processes such as LDED and LPBF. This method leverages the acoustic signals produced during laser material interactions which encode valuable insights into physical phenomena such as melting, solidification, crack propagation, and pore formation. Lastly, laser line scanning is being used as an in situ monitoring process to scan each surface layer of the product as it is being printed to create a topography map of the surface and feed this information to the adaptive control system. This will reduce defects as adjustments can be made during the manufacturing process. Without this capability, the defects may be detected at the end of the manufacturing process, resulting in scrap. Or the internal defect could go undetected, even worse, resulting in a delivered product of inadequate quality. When it comes to practicality and ease of implementation, in situ process monitoring techniques are the most widely adopted and integrated in the current industry. A digital twin is a virtual representation of a physical product that encompasses the manufacturing process of the product, the dynamics and behavior of the physical product, as well as the product itself. This digital twin, or DT tool, was developed to allow a manufacturer to use tools such as the Internet of Things to fully optimize and track the manufacturing process of a product and how it responds to constantly optimized controls. More specifically, DT was developed by NASA to track and analyze the performance of a satellite by using the digital twin version of the satellite while the physical satellite was in flight. The development of a DT consists of 5 steps. The first step is data collection. During the data collection phase, the data is acquired from various sources including sensors, monitoring systems, and simulation tools. This dataset consists of process parameters, material properties, environmental conditions, and machine performance. Using this data, the next step is model development, where the data from all variables will be used to develop a mathematical model and optimize metrics. The calibration and simulation phase are critical to ensure the model provides a consistent and accurate product output. In additive manufacturing, it is critical in this phase to test the strength and integrity of the material since it is formed by bonding layers of material together to make geometry. Next, the actual digital twin is created using the data and the calibrated model to create a three-dimensional virtual system. This virtual system consists of the product itself, all its manufacturing processes, and even virtual people. The software offers a sophisticated hardware motor, a powerful system of events, an animated system, enhanced parameters for lighting, and the possibility of incorporating customized software logic using a programming language. Lastly, the digital twin is observed for real-time tracking and monitoring. Sensors and the IoT continue to provide data to the digital twin, which is used to continuously adjust and improve the model based on machine learning. Artificial intelligence is beginning to be implemented into digital twin as well. San Pedro has recently developed a digital twin system that uses the 3D Amplify AI algorithm to detect defects in a 3D printer. A digital twin of an additive manufacturing process would consist of a virtual environment of structure, components, and functionality of the 3D printer. Using sensors, this DT environment would optimize things like nozzle temperature, bed movement, printing speed, layer thickness, and other variables. Soon we will see additive systems on the market with built-in digital twin systems included in the software and printer package. The additive manufacturing industry is growing at an extreme rate. As innovative technologies develop, what was recently new tech becomes outdated and it can feel difficult to keep up. Integrating new adaptive controls into existing additive manufacturing systems can pose a challenge. Many legacy additive machines were not originally made with adaptive controls in mind, making them difficult to retrofit. These control algorithms can also only be effective if they can handle unique environments, differences in machines, and the multitude of varied materials that the machine is capable of printing. Another challenge is the ability to compute and process high data volume. The system will require robust data processing for substantial amounts of data and be able to handle complicated algorithms. The storage space is also significant, as the system will also need to be able to store large data sets without slowing down the real-time adjustments that are being made to the process. Implementing AI into a production environment will require major advancements in computing power and storage needed to fully integrate and automate adaptive control systems. In conclusion, the current state of adaptive controls has played a large part in the rapid progression of a young technology in additive manufacturing. The industry is turning from what was once a fun hobby or a tool for rapid prototyping into a production manufacturing tool with capabilities unrealized prior to its time. In situ controls like optical monitoring, acoustic monitoring, and laser light scanning have been implemented in laser additive manufacturing machines to analyze and identify internal defects in real time while parts are being manufactured. Tools like digital twins have been able to take the in situ tools to use IoT, AI, and machine learning to take this data and drive continuous improvement in 3D printing. The biggest limitation as we move into Industry 4.0 is the necessity for computing and the current cost of AI technology. As new breakthroughs are made in the technological world, these limitations will dissipate and we will begin to integrate rapidly and efficiently into the additive manufacturing industry.